This paper is about the optimal scoring rules for multidimensional effort. I'm Yifan Wu. This is my joint work with Jason Hartline, Liren Shan, Yingkai Li. So proper scoring rules are used to evaluate a prediction distribution. So the prediction is evaluated against a random state from the distribution, and the output is a real value score. So the definition of properness is when expected score of true distribution of the random state is higher than any other distribution. With this definition, the proper scoring rules are widely used in machine learning as a loss function. When the learning algorithm outputs the true distribution of the random state, the loss reaches the maximum. And also in mechanism design, to elicit information from a strategic agent who wants to maximize the expected score. For example, you can use it to score students in exams so that students can tell you their belief of the ground truth answer. So some scoring rules are bad in terms of mechanism design. So the agent can learn by doing Bayesian updates. After doing Bayesian updates, there is an increase in expected score. However, for some scoring rules, that increase may be very low. So if the agent has to pay a cost to acquire the information and do Bayesian updates, if you are using a bad scoring rule, then the agent is not incentivized. So previously, we have a work that designs the optimal scoring rule under binary effort, where binary effort means the agent can only select to Bayesian update or not to Bayesian update, which is exerting effort or not. We show some commonly used scoring rules can be bad. For example, if that effort is reviewing for the exam and you have multiple assignments for the exam, a common practice is separate scoring rule, which means you have separate scores for each of the assignments, and the total score is the sum over them. We show this is bad compared to optimal scoring rule. And in this work, we consider the multidimensional effort model, where there are n tasks, and the agent can separately select to Bayesian update on each of them. Let's think about how to incentivize students to do assignments. Suppose there are n assignments, and the student learn by selecting a subset over the n assignments to do. And doing each assignment induces a cost CI, the student pays the total cost. Only after paying the cost, the student learn the ground truth with some probability. And the instructor has a budget from 0 to 1 to score the student. The instructor also has a value over the assignments that are done. So the goal of the instructor is to design a scoring rule and also a problem set so that the student is incentivized to do every assignment in the problem set. And also the value over the problem set is maximized. So you can see this is a variant of the knapsack problem, which is a classic algorithm design problem and has good approximation guarantee. So our problem is the optimization problem, where we want to design a scoring rule in polynomial time, and also we want to design a problem set for the student. There is an issue of incentive compatibility, where a strategic student can select a subset of the assignments that are posted, and he may also misreport the learning outcome by guessing. And we assume the strategic agent is Bayesian. So we design two scoring rules and take the better of the both. The first one is a truncated scoring rule, where we post separate scores on each assignment I, and the sum over the scores may exceed 0 and 1, but eventually we truncate it into 0 and 1, the budget. And the other one is the threshold scoring rule, which means you score 1 if the student gets at least one assignment correct and others are not wrong, and score 0 otherwise, which means the student either gets something wrong or doesn't get anything correct. So our theorem says the better of a truncated scoring rule and the threshold scoring rule with a properly designed problem set achieves a constant factor of the optimal value, which is a constant approximation. Other results in the paper include the empty hardness of our problem and by criteria approximation, which means we can achieve the optimal objective by inflating the budget 0 and 1 to some constant factor. And under a different model of sequential response, where the agent can look at one assignment, obtain the information, and decide whether to go next, we show the same scoring rule is also a constant approximation. And that's all. Thank you.